finally time. It's finally time to do Lagrangian mechanics. I'm super excited. So if you're following along with my classical mechanics series here, I've done a bunch of stuff. The playlist is down below, but let's just jump into it because I'm excited. And I'm not going to derive everything, but I'm going to show you how to use it because it gets a little bit complicated, but also awesome. Okay, we already did this problem. This is a mass on a string. We call it a pendulum. And I mean, it's actually not an easy problem. Even if you put it in an introductory physics course, you can say, oh, it's like a simple harmonic oscillator. And true to the first degree. But other than that, it gets really bad. So why is it hard? Well, the reason is that if we have this downward gravitational force, mg, and then I have the tension in the string like that, well, I can calculate the gravitational force, mg. It's not hard. But I can't calculate the tension. I don't have an expression for the tension. The tension is a problem. The tension is what we call a force of constraint. Remember that we have two kinds of forces. I call them calculated and constraint. So calculated forces, the gravitational force, even the air resistance force, the force due to a spring, the electrostatic force, the magnetic force, things like that. I have an equation. It tells me this is the force. And then I have constraint forces. These are forces that prevent the object from doing something. This string prevents the mass from getting further away than r. So it constrains the motion. The other classic one that you're going to see is the normal force. When a block slides down a plane or even a curved plane, well, that force, the normal force, just prevents the block from going through the thing. So it could be any value. We don't have an equation for it. And that makes Newton's second law really difficult because we don't have an equation for that, right? Because I like to say this, F net equals ma, but if I don't have an expression for the net forces, I can't find the expression for A. So it's a problem. Now, we did solve this problem, and I know I'm going to get into Lagrangian. Just calm down, we're going to do it. We did solve this problem by using polar coordinates. So in polar coordinates, just as a reminder, I'm not going to go through the whole detail, I can say the forces in the r direction is m times r double dot is minus r theta dot squared, and then the net force in the theta direction is going to be m r theta double dot plus 2 r dot theta dot. Whew, I don't know why I forgot that. And in that case, I can say, well, I don't really care about this r direction because r is constant. So that's 0, that's capital R, that's 0. So I only get two terms. And I'm going to skip to the end. We get the following equation. Theta double dot is negative g over r sine theta. That's what you get. Okay, because you get the sine theta from the component of the gravitational force in the theta direction. And that was the equation of motion for a pendulum. We're going to get back to that. Okay, so well, you can do it, but it's not trivial. If you want to do it another way, you can actually find the value of the tension force, but you got to use centripetal acceleration and conservation of energy. It's not that much fun. Okay. Now, let me just imagine another situation that I will set up later that would be pretty much impossible. Let me just erase this. So you could do the pendulum, and we did. We did do it. Okay, but here's another problem. Riddle me this, Batman. Oh, it looks like a pendulum, but it's not. It's a double pendulum. Okay, so the problem with the double pendulum is that I don't know the tension here, I don't know the tension there, and this tension, this mass is not even moving in a circle. So even if I wanted to use polar coordinates, I couldn't, right? This is moving in a circle about that mass, but that mass is moving too. So even in Lagrangian mechanics, this is a pretty hard problem, but it's not conceptually difficult. Okay, that's a problem that I'll show you how to set up. Well, it turns out that if I have this pendulum, we're going to go back to the pendulum, and I will solve this. I can solve this through the principle of least action. So we define the action as the integral from t1 to t2 of some variables, it doesn't even matter, L of q dot t dt. So it's a path integral over time. And what's L? And I know I'm like magic stuff here, but L is called the Lagrangian, and it's the kinetic energy T minus the potential energy. And so that comes about from some strange things. Surprisingly, Veritasium just did a great video on this equation. I'll link that down below. You should watch it. It's way better than anything I would do. I'm focusing on the do, right? So this is the action. So Lagrangian mechanics says that the actual path in time, this function of q and q dot, is such that this path, this action is minimized, not technically minimized, but stationary. Okay, so we've done max-min problems at some point, right? You take a function and then you say, okay, where is that function the smallest? So if I did the area of a perimeter or something like that, so area as a function of length, and it goes like this, maybe even goes like that, and I say, oh, look right there, the derivative is 0, so that's a local minimum, and then we can find out if it's the absolute minimum and all that kind of stuff. That's the max-min problem. This is a little bit different because it's the integral. We want to find the function that minimizes the integral. So I'm going to give you the classic example of the how do you find the path between 2 points such that a block will slide, we'll call this P1, P2, in the least amount of time. So you could have a block slide straight down there, but it turns out that this path is faster. Okay, so, but how do you find that path? I can find the time along some path, but how do I find the path? That's the problem, right? How do I find a function that minimizes an integral? Because that's what we have here. We have integral that we want to minimize the result by changing that function. And the result is called the Euler-Lagrange equation. So this will give a stationary action if the following is true, and this is the part that you really want to look at. The partial of L, these are just some variables, q, q dot, and remember that dots are derivatives with respect to time and time. So the partial of L with respect to q minus the derivative of the partial of L with respect to q dot is 0. That's our Euler-Lagrange equation, and that tells us how to find the relationship between q dot and q for some variable. Okay, that looks very complicated. Why do we even care? Well, this actually does something really great for us because q and q dot can really be any variables, and what we can do is define our system in terms of these variables so that we don't have to worry about forces of constraint. I think we should just do a problem. Let's just do, I'm going to do a ball tossed in the air, and then we'll do the pendulum, and then I'll set up a couple more problems. So let me put this over here. This is my Euler-Lagrange equation. The partial of L with respect to Q minus the derivative with respect to time, partial of L with respect to Q dot equals 0. That's important. Okay. Oh, and I need to say L is T minus U. Okay, that's the Lagrangian mechanics right there, that whole thing. So let's take the following situation. I have a ball, and I throw it up with some initial velocity v0, and this is just in one dimension. Okay, so actually I can describe the kinetic and the potential energy of this ball. So let's say this is y equals 0. Then in that case, the kinetic energy is 1/2 m y dot squared. Right, that's kinetic energy. I can describe the potential energy, m g y. I can find the Lagrangian, 1/2 m y dot squared minus m g y. Now I can use the Euler-Lagrange equation to get a relationship between my differential variables and my other variables, and that's what I want to do. So let's go ahead and apply this. I'm going to say the partial of L with respect to y. If I have more than one variables, you can do it with more than one variables, but I'll save that for a later case. Okay. You can do this for as many equations, for many variables as you want. So I'm going to take the partial of L with respect to y, and I'm just going to write it out. The partial of L with respect to y, Here's my L. I'm looking for y. So it's a partial derivative. So where is there a y? Right there. So I have the partial of negative mgy is going to be negative mg. Now let's take the partial of L with respect to y dot. So there's my y dot. That's a partial, right? I can ignore everything else. So it's raised to the power of 2, so I'm going to bring down the 2. I have 2 over 2 my dot. So it's just going to be my dot. Now, through the power of chalk, I'm going to take the derivative, the time derivative of that. So in this case, mass is constant, so I don't need to take the time derivative. And the derivative of y dot is just going to be y double dot. Now I can put this all together. So I have this negative mg, g minus my double dot equals 0. Well, I can add that to both sides, divide by the mass, and I get y double dot is negative g. Okay, now you think, hey, but we're not done. You didn't finish the problem. Well, I got to the same spot that we did when we had Newtonian mechanics. It's a differential equation. Lagrangian mechanics doesn't give us the full solution. It gets us the differential equation. And then we have to use our normal methods to solve that. So, I mean, I don't want to go through all the details, but if you integrate this once, I get y dot equals negative gt plus v0, right? We've done that before. Integrate again, and I get y equals negative 1/2 g t squared plus v0 t plus y0, and then you have an equation of motion. Pretty cool, huh? Pretty cool. And it's important to do something like this because we already knew the answer. And if you can do it a different way and get to the same thing, it's like, hey, it's not so bad now, is it? Okay, I told you we'd do the pendulum, and there are a couple tricks that we need to do. Okay, so I'm going to do the pendulum now, and then I'm going to show you some other things that we could do. So we still have the same thing. Let's look at the pendulum. One of the things that you always want to think about when you start a Lagrangian mechanics problem is how many degrees of freedom, how many variables do I need to determine the state of the system? And in the case of a pendulum, I only need one. I only need one variable, right? I can describe the exact position of this with just theta, and now I'll need theta dot too. So I don't need to use polar coordinates exactly. I don't care about r. It's constrained, right? And in fact, imagine, well, I'll do that problem in a little bit. Let's just go ahead and do the pendulum problem. So here is my pendulum. What do I want to do? Number one, I want to pick my variable. I'm going to use theta for my variable. I'm not going to use x and y. I'm going to use theta. Now the next step is to write the Lagrangian. And to write the Lagrangian, you notice I spin around because I don't want to get tangled up in my cord. So I need the kinetic energy and the potential energy. So there's my theta. So I can write kinetic energy. Now that's not so trivial, right? These can be tricky. So what I want to do is to write these in terms of Cartesian coordinates because I know what they look like in Cartesian coordinates. Some people would say, well, you can kind of just use your intuition. I know what the velocity in polar coordinates looks like. That's fine, but sometimes you don't know that. So let's do it the long way. So I can say t is 1/2 m x dot squared plus y dot squared, right? It's the velocity. And it could be, in Cartesian coordinates, I have to realize it's moving in two dimensions. And then u is mgy. Those are my kinetic and potential energy. And I didn't say this, but we use T for kinetic energy. But I did that in the previous video too. So, okay, well, now all I need to do is to get x and y in terms of theta. So over here in this problem, and I don't even have to use the proper coordinate system or anything. I can do whatever I want. But I'm going to call that x and that y. So I have x equals r sine theta. Y equals negative r cosine theta. And you'll notice I'm using r for the length of the string instead of L. I wonder why. That's why. You can do whatever you want. Okay, so now I have those variables. What I can do to get x dot and y dot, I need to take the derivatives of these. So let's take the derivative of x. X dot is going to be the derivative of this with respect to time. Well, r is constant, so I don't have to worry about that. I do have to take the derivative of sine theta. I get cosine theta, so r cosine theta. But wait, I have to take the derivative of theta too, so I get theta dot. Over here, I'm going to take the derivative, and I get r sine theta, theta dot. The derivative of cosine theta is negative. Oh, I got those backwards. X is sine. Yeah, that's right. Okay. Now, oh, that's theta. That's y dot. Now I can square these two and add them together. So let's just do this in one fell swoop. X dot squared plus y dot squared is going to be r squared theta dot squared. Factor out the cosine squared theta plus sine squared theta, right? Because they both had an r and a theta dot, and I factored those out and then squared them that way. And then I squared them first, and then I added them together. And then this is just 1. So this is going to be r squared theta dot squared. Yay. Now, for u, I can do that pretty easily. U is just going to be mg, and then y is negative r cosine theta. Now let's put it all together. L is 1/2 m r squared theta dot squared minus u, but u is negative, so I get plus mg r cosine theta. So now I have my L. Okay, let's write that up here. 1/2 m r squared. Can you see that? Yep. R squared theta dot squared plus mg r cosine theta. Okay. Now we can take our derivatives. And I'm going to do it in steps just like I did before. And again, you may be thinking, this is stupid where he did this. We don't need to do it this way. We're practicing because there are problems that you cannot do double pendulum in another way. So I'm going to take the partial of L with respect to theta. I only have one variable, right? So the partial of L with respect to theta. So there's no theta, no theta, no theta, no theta. Boom, there's a theta. So the partial of cosine theta is negative sine theta. So I get negative mg r sine theta. And I don't take the derivative of theta because I'm taking the partial with respect to theta. So that's it, I'm done. Okay. Now the partial of L with respect to theta dot. No theta dot, no theta dot, boom, there it is. So I use the power rule, bring that down, I get m r squared theta dot. Now I can take the derivative of both sides with respect to time, the absolute derivative, and constant, theta double dot. Now putting this together, I have negative mg r sine theta minus m r squared theta double dot equals 0. So m r squared theta double dot equals negative mg r sine theta. Mass cancels. That cancels with that. Theta double dot is negative g over r sine theta. I have the exact same differential equation I had before. And I'd still have the same problem solving that, right? And you could, if you have a small angle approximation, you can say sine theta is theta, and then this becomes theta double dot. It's just a sum of sines and cosines. If you want to solve it numerically, you could. But that's the differential equation. It's about getting that differential equation. We got the differential equation. Okay. Let's look at the double pendulum. I have a solution to the double pendulum if you really want it, but you probably don't. Okay, because it gets nasty. I'll tell you right now, it gets nasty. But let me tell you how you would set it up using the Lagrangian, because you can't set it up using Newtonian mechanics. I don't think. You can, but it is not easy. It's very, very, very non-easy. Okay. So let's just add on to here. I'm going to put it right there. So here, this is R1, R2, M1, M2. And then that's theta 1. And let's call this theta 2. So I need two variables in order to completely determine the orientation of that double pendulum. So I need theta 1 and theta 2. Now, how do I get the kinetic energy? So I'm going to have two Euler-Lagrange equations. I'll have one for theta 1, I'll have one for theta 2. But I wanted to set up, how would you even find the kinetic energy? Okay, so here the beauty of this is I can still find the Lagrangian and the kinetic and potential energy using Cartesian coordinates. So for this one, I'm going to say the x1 dot, y1 dot I can find. same as before. I can say x1 is r sine theta 1. y1 is negative r cosine theta 1. And then I can take the derivatives and all that stuff, and that's fine. Now for this one, mass 2, I can find its x position. I can say x2 is going to be equal to r2 sine theta 2 plus x1. So whatever this angle is, I just add in the x value over here. And I can do the same thing for y2. y2 is negative r2 cosine theta 2 plus y2. Now when I take the derivatives of this, I'm going to have to take the derivative of x2. I'm going to get a theta 2 dot and x1 dot. I'm going to get an x1 dot from up there. So things get messy very quick, okay? But you can do it. That's the point. So you can do the double pendulum, write down your kinetic energy, write down your potential energy, and everything is great. Let me show you another example. I'm not going to solve it. I'm just going to set it up. I'll solve these in another video. This is Introduction to Lagrangian Mechanics. This is not solve every single Lagrangian mechanics problem. And I just made this one up, but I think I've seen it before. So imagine I have a frictionless cart with a mass m1, and it has a spring connected to a wall. And then over here is a pendulum. I mean, it could be a pendulum, but this is confined to move up and down like that. And now the first thing you would see here is like, how many degrees of freedom would I need to explain this system? And the answer is 1. I only need one variable, right? Because if this moves that way, that's going to move down that way. So I could call this S. And then I could get the kinetic energy of this plus the kinetic energy of that. They both have the same S dot in there. I could find the potential energy of that spring, the potential energy of this mass, and I could write the Lagrangian and then write down the Euler-Lagrange equation. Let me set up one more example because I do like this one, and I will do this one later. So imagine that I have a pendulum that looks like this. So here, this is called a jiggle pendulum. So it's connected to this point right here, but this thing can oscillate up and down like that. Okay, and then this is theta. And I will do this problem because it's one of my favorites. So here I could say the y of this value, y is going to be equal to, that's r, it's going to be equal to negative r cosine theta, just like before, but plus some a cosine omega t term, right? Because that thing oscillates up and down. And then x is just going to be r cosine sine theta. But now when I can do the same thing. I can take my derivatives and find my kinetic and potential energies, but I can get this extra term in there. And then we're going to get a differential equation. That differential equation, then we have to solve it some way. We can model that in Python, but we'll definitely do that problem too. Now, one of the things I didn't point out, one of these two things I didn't point out. Number one, what if I want the force of constraint? What if I want to find the value of the tension? There is a way to do that. Two, what if there's friction in the system? Okay, if there's friction in the system, it's not going to happen. Okay, so Lagrangian mechanics isn't always a solution. If you know the values of the force, if you know expressions for the force, use Newtonian mechanics. If you have force of constraint, you don't know what those forces are and you don't care what they are, and there's no friction, then you can use Lagrangian. But you really have to practice this a lot to do it. So this is the Lagrangian. That's the Euler-Lagrange equation, and we can use that to find our equation of motions. Whew, okay, I know that's a lot, but I'm excited about doing some problems.